Stability means a process is behaving in a predictable way, but it doesn't necessarily mean it meets the customer expectations. Process capability measures to what extent it can satisfy the customer requirements. The first step for process improvement is to achieve stability. We analyze this with statistical process control. As a result of this analysis, we may detect out-of-control situations due to special causes. In this case, we need to resolve these causes to make the process stable. Once the process is stable, we can find out to what extent is it able to meet customer expectations. This is done by measuring process capability.
You can see this article in polyhedrica.blogspot. Download this Excel file capability.xlsx from OneDrive with the examples we will use to your PC before you run it. In sheet diameter in column A, we have 500 measurements of a critical diameter. After being confident that our process is stable, we can characterize it with descriptive statistics in Excel data analysis. These are the resulting diameter basic statistics in sheet descriptive statistics. All these statistics are meaningless unless our process is stable over time. This we can check with a Statistical Process Control (SPC) analysis. See sheet SPC diameter. We see no out-of-control symptoms, so we conclude this is a stable process. We can, then, assume that our statistical analysis of this sample can be applied to the population. The histogram gives a graphical representation of this variable. In Excel data analysis, we select histogram. See sheet frequency distribution. We see a bell-shaped distribution typical of a normal Gaussian distribution. It is quite symmetrical, and its mean, median, and mode are very similar. This is a very common distribution in nature and in many process metrics. We want to know, to what extent is our diameter distribution normal Gaussian? We do this normality test in sheet basic stats diameter. We can confirm this diameter data follows a normal distribution. P-value 0.466 is greater than alpha 0.05. Meeting this normality condition is a prerequisite for the validity of our SPC test we have just performed. In sheet lead time, we have collected process lead time, hours. We do the same analysis. In this case, we see a very skewed distribution. We also notice that mode, mean, and median are quite different from each other. Let us check now manufacturing lead time normality, sheet basic stats lead time. In this case, the distribution is very skewed. So, lack of normality is confirmed. P is equal to 0, which is below 0.05. This is something common in time measurements. The reason for the skewness of time distributions is that 1. There is always a physical limitation, which makes it impossible for a time metric to be below a certain limit. In this example, this limit may be around 8 hours. 2. There is no upper limit. Occasionally things may go wrong, and time can become very large. All processes have a customer, either the final, external customer or an internal customer. In our process metrics, we need to know not only the nominal value required by the customer, but also the spec limits. For a mathematician, the nominal value may be enough, but in real life we know it is impossible to exactly meet any real value. There is always an error, even if it is just a few microns. The spec limits indicate where the customer starts having real problems when using our product. In some metrics, such as a dimension, there are lower and upper limits. In other metrics, there is only one limit, upper or lower. Customer specs are still required in the times of Six Sigma, but their interpretation has changed. The classical approach was like a football goal. If it goes within the limits, it counts as a goal. In the new approach, being within the limits is not enough. You must keep away from the limits to avoid falling over to the sharks. We must prove to our customer that our process is very unlikely to produce a single part outside the specs. We use capability metrics to estimate to what extent is our process able to systematically satisfy the customer, meet the specs. Imagine you measure a critical dimension of the parts you just received from your supplier, and they are all within your spec limit following this distribution. In the old times, you would just accept these parts since they all meet the specs. But those parts close to the spec limit will probably cause you problems. Also, looking at the strange shape of the distribution, you can guess that your supplier is producing bad parts and then removing them before sending them to you. This is a waste that you will eventually end up paying for. The process used to separate the good from the bad will have escapes, so you will also receive some faulty parts. Assuming our process is stable, the histogram characterizes the process behavior. We need to compare this with the customer requirements represented by the spec limits. Any parts produced by our process, beyond the spec limits imposed by the customer, will produce dissatisfaction. Process capability measures the ability of the process to systematically deliver within the spec limits and therefore satisfy the customer. This index is an estimation of the ability of a process to satisfy its customer. The Process Capability Index CP is the rate between the spec range specified by the customer spec limits and our process variation measured by 6 times its standard deviation. We can see some examples of CP values. A value of 1.5 or above is considered good. Here, we have good CP value, small dispersion, and still produce many defects, because the process mean is not in the center of the spec range. We need another capability metric to take this into account. CPK considers the position of the distribution mean with respect to the spec limits. It calculates the distance from the mean to its nearest spec limit divided by 3 times sigma. When the distribution is centered in the spec range, CP is equal to CPK. If not, CPK will be lower than CP. Centering the distribution can, sometimes, be achieved by an adjustment. This will improve CPK, making it closer to CP. Improving CP implies reducing the standard deviation, which is typically much more difficult. We want some variables to be as high as possible, such as profit, customer satisfaction, and capacity utilization. In this case, we only have a lower spec limit. Some, we want as small as possible, such as cost, lead time, and inventory. In this case, we only have an upper spec limit. In the case of one-sided specs, CP makes no sense, since we can't talk about spec range. In this case, we just use CPK as shown. In this case, CPK is well below 1.5. This means the process is not capable. It will, too often, cause customer dissatisfaction. The process needs to be stable and follow a normal distribution. The specs must be meaningful to the customer. The number of measurements should, at least, be 50. We will now use the data from our previous diameters example. Let us assume spec limits of 95 and 110. But before we do that, we need to make sure that the process is stable. We will use a variable's SPC chart for individuals. A condition to use this chart is that data follows a normal distribution, which we already confirmed before. The SPC chart doesn't show any out-of-control symptoms, so we can go ahead and calculate the capability indexes CP and CPK. We apply the formula to calculate CP, spec range divided by 6 sigma. To calculate CPK, we select the spec limit closest to the mean, which is the lower spec limit of 95. We divide the distance between the mean and the lower spec limit by 3 times sigma. Both values are totally unacceptable. We can expect many defective parts. The fact that CPK is lower than CP indicates that the process is not centered in the spec range. A target for a 6 sigma process is a CPK of 1.5. Let us now calculate the capability of our previous process time data. Let us assume that we have agreed a maximum lead time of 50 hours with our customer. So, this will be our upper spec limit. We have no lower spec limit. One condition for our capability calculation is that data should follow a normal distribution, which we checked before that this is not the case. We expect lead time to follow a skewed distribution, therefore not normal. In this case, we can look for a data transformation that will make it normal. We have placed the lead time data in column A of sheet Box-Cox. Now we will use Excel Solver to calculate the value of lambda in cell I8, which produces the maximum value in cell I6. The resulting value is minus 0.348. In column F, we have the transformed data, which is just lead time to the power of this lambda value. We will now check if this transformed data follows a normal distribution by copying it to the basic stats transform sheet. We have indeed achieved normality. P is equal to 0.717, which is greater than 0.05. We now check for process stability with the transformed data in SPC transformed sheet. The process is stable, no out-of-control alerts. We must notice that as time increases, the transformed values decrease, so the upper spec limit will be transformed into a lower spec limit. The upper limit of 50 hours becomes a lower limit of 0.256. So, the resulting CPK is 0.56, which is unacceptable to the customer. This CPK means that 4.7% of deliveries will be late. So far, we have been dealing with variables, but sometimes we only have attributes such as pass or fail or defects per unit. Variables can be converted to attributes. For instance, we can count the number of items out of spec. Going back to the diameter example above, we can compute the percent of parts above the USL and below the LSL. 31.1% will be below the lower limit and 14.8% above the upper limit. So the proportion of good parts, called yield, is 54.1%. We can see this graphically with the histogram. In this histogram, we can see the proportions of parts within the limits and out of spec. With attribute metrics of the type of pass or fail, we have a binomial distribution, and we can measure capability with yield, proportion of pass. Another attribute capability metric is number of defects. In this case, we have a Poisson distribution, and we can use two capability metrics, DPU and DPMO. In this example of one defect in 3 boards, DPU is 0.33 defects per board. From the board assembly process point of view, there is one defective component out 36 components used, which is 27,777 defective components per million opportunities. DPU, defects per unit, is a metric from the customer perspective. DPMO, defects per million opportunities, is a useful internal metric for process improvement. A capability metric used for business processes is sigma capability. This metric is equivalent to CPK when there is only one spec limit. When there is only one spec limit, sigma capability is equal to 1.5 plus 3 times CPK. A 6 sigma process is one with sigma capability equal to 6. This is equivalent to a CPK of 1.5, or a 3.4 ppm defectives process. You can use this capability metrics conversion table by filling your number to convert in the corresponding yellow cell, and the equivalent metrics will appear in the same line. Yield and DPMO are attribute metrics. Sigma capability is used for business processes and CPK for manufacturing processes. Be aware that when converting between CPK and attributes, we are assuming a single spec limit. Let us now compare several situations of process stability and capability. In an ideal process, the process is stable over time. There are no out-of-control symptoms in the SPC chart, and the spec limits are beyond the control limits. In this case, the operator should keep it in control. This is a stable process, but unable to satisfy the customer requirements. It is up to the process owner to improve this process. This is a capable process, therefore able to satisfy the customer, but it has gone out of control. In this case, it is the operator who must react the moment this happens to put it under control before it can affect the customer. Process not capable and out of control. The process owner must change the process to meet the customer specs. Then the operator must make sure he keeps it under control. These are some conclusions. Process capability measures the ability of the process to meet the customer requirements. The customer may be the final customer or the next process using our output. Meeting the specifications is not enough. Capability ensures they will also be met in the future. A capability study requires the process to be under statistical control. The process must follow a normal distribution for the capability indices to be valid. Data can usually be transformed to achieve normality and enable a capability study. SPC is used by operators to keep the process in control. Process capability improvement is the process owner's responsibility. Process data analysis can be used to improve capability. Design of experiments may also be used. These are some articles to analyze and improve process capability.